So that's down here. Down exam. Okay. So yeah, I will include them into hints as soon as the exam is complete. And let's just say for whatever reasons, let's look at summer semester 23 and immediately the solution. Okay, and then we have here, maybe you all will recognize also this from some exercise sheet. We have here a motor, a shaft which rotates, and on this shaft we see here an unbalanced mass, and this rotates. And we said we can model this first mechanically as ideal elements, as a link where we have attached a larger mass for the motor block, a smaller mass than for this unbalanced mass. Then we have fixing here to the ground with some damping B and some elasticity K. So we have a damper and a spring here. And we are interested then in vertical movements. That means we also have here this reference frame for movements x or velocities or accelerations. And okay, so possible questions here. We have a lot of forces and we need a balance of forces, so an equation for this balance. And what I actually expect of you would be just the first part here, that you say we have one external force, and this comes from the rotating unbalanced mass. It's the centrifugal force, and this is balanced then by inertia from the two masses. So that's the first two terms here, and the friction force from the damper and reaction force from the spring. So actually I just want this part here, that's really needed. And the other one is just for information also, just to be clear here, it's not necessary to write that. There was no question what this value is. Okay, then the next question was draw an equivalent electrical circuit. For the mechanical model, use the Fi analogy and note here formulas I just said. So I'm interested, for example, a capacitor could be larger or smaller with the corresponding mechanical quantity. Here the capacity is proportional to the mass, but for example here the resistor is indirectly proportional to the damper constant. So I wanted to see this 1 over, or is it proportional? Okay, so that's the element according Fi analogy retains the same topology. So in the mechanical model we have parallel forces, and that becomes parallel elements. And then a question here about a source transform, because we said there is another viewpoint, let's say. We could say this, you replace the centrifugal force with the movement of this unbalanced mass, and well, this is then it's kind of mass, and it's kind of mass, and it is moving. So we have a series of mass and a velocity source. So that's one possibility to interpret this, and we have the centrifugal force acting in parallel to the inertia of the mass. So that's the second viewpoint. Electrically, we could say this is a series of a voltage source with a capacitor, or it's a current source with the same capacitor but in parallel. And then we could say something about the values between U0 and I0. that might be an additional point, but okay, so for 2 marks, that will be enough. But you might remember that in the exercise sheet, we said a little bit more about the amplitudes of the velocity and of this source. It's not necessary here because it's not asked for. Okay, so just to give you an idea, what's necessary and what is not necessary. Then we have another example here, thermal conduction. We see here the real situation. We have a boiler with water inside, and we have here a heating where we apply electric power. The boiler is insulated, but still we have transfer of heat. So first of all, the water has a certain heat, and part of that will go into the case. So that's one transfer. And then from the case over to the ambient. That's the second transfer. And each transfer can be described with a resistor. So we have a stream of power, which can be modeled as a current source, so heat power. And we have 2 resistors, and then we are here initially at ground, that means in the ambient. But we have more, we have 2 capacitors, and now we should explain the meaning of these capacitors, but also that of I0. Ground was already set, corresponds to ambient temperature. And I0, okay, that's dissipated heat power. But the capacities itself, well, because the water itself has a mass, it means the capability to store more heat, but also the case has some mass. These are modeled then as capacitors or thermal capacities. Okay, so just some keywords. You don't have to write long sentences and long explanations, they're just short keywords. Okay, then we can do something with the model. For example, here we can calculate average electrical power we need in order to keep a constant water temperature. Constant is a very important word here, because it means if nothing changes, we can simplify our circuits. A capacitor is then simply a disconnection, so it's as if it is not there. And an inductivity would become a short circuit. But we don't have thermal inductivities, so it's just here the capacities can just be neglected. They have no effect on the static result. So it's just the current source and 2 serial resistors towards ground. That is what remains here. And then we can just add the 2 resistors to one value. And okay, what do we know? 60 degrees is the temperature of the water. 20 degrees is the temperature of the ambient. So there's a difference of 40, let's say 40 kelvins. And that acts across the 2 resistors. Okay, we know this, we know also values for the resistors, so what we can calculate according to Ohm's law is this power corresponding to a current. So, Ohm's law here means the resistor is voltage divided by current, okay, so that's electric form, and this current would be voltage divided by resistor. Okay, and then just insert the values and we get something. Okay, so that now ensures that we have always a temperature of 60 degrees inside, but now we switch off electrical power, and well, what happens now is we have dynamics, so we need our capacities again. We have no more source is 0, so it just vanished. We have this capacity 1 that corresponds to the mass of water, which has a certain temperature. we have again two resistors and we neglected here in between capacity 2. Why is that? Because here it was that C2 is negligible. And well, yeah, that makes sense. So the case is just something brass plus insulation. It doesn't have so much weight, and its heat capacity is also not so large with respect to water. So you could neglect this thermal capacity of the case itself, and you don't have to think yourself about that. Here it's in the text. C2 is negligible. Okay, so still we have just two serial resistors here. Well, and then we have a loaded capacitor, and that is discharged through R1 and R2. So we get an exponential curve. I think we have covered that in one of the first slides. It's a kind of step response. Whenever we have a constant with a certain change, but then we have constant inputs. As a first order system, and a capacitor is one such, we get exponential curves. Okay, so depends on time, and time is divided here by the time constant. We used that a couple of times. Yeah? R multiplied with a C is a time constant, and here the question is calculate the temperature drop in the water after 24 hours. Okay, so we insert for the time 24 hours. We also calculate this time constant. All the values are, not all the values are given. So the values of R is given. The value of C1 we need to calculate. So in the slides we had decomposed this into a specific thermal capacity, depends only on the material, and we multiply this with the mass, in this case of the water. Okay, 400 liters of water has a mass of 400 kilograms, and this was a value given here, divided by kilograms. So just multiply these, and this is the value of the capacitor, and let's just say the units will fit. Careful, there's a K. So that means 1000, factor 1000. Okay, and then we have R times C is then 420,000 seconds, and a day, 24 hours, has about 86,000 seconds. So we have an exponential drop of minus time divided by time constant. So something. Okay, so what's really important is here to see it's a first order system, and when we charge or discharge this, there are exponential functions. Then you can solve everything there. You know that unfortunately we may not take anything into the exam except for dictionary or of course the calculator. So we include then a formulary, and this could be something like this, could be more. We will give a hint what will be included in this formulary, so that you know what you have to learn by heart and which formulas are already there for you. Okay, so that was a possible first question. In the second question, we asked them more about MATLAB and Simulink models. And here, for example, could be something similar. So we have a differential equation. Sometimes it's two coupled differential equations, depends. And you should model this in Simulink. So I don't care how you draw exactly these blocks. Just make sure that you understand which block is which. In Simulink, actually, an integrator has this text 1 over Laplace S. But you could also write int, for example, let's have a text int, when I understand, that's the integrator. Or integral sign, everything fine. Just make clear where is an integrator and where is a derivative. And we do need a derivative here for the input variable, because we don't just need it itself, we also need a derivative of the input. That is really done with derivative blocks. Okay? And everything that has to do with the output, we need to send through integrators. Okay, then the rest should be clear. Then you could also determine a transfer function. So there's a little bit of mathematics here, but I think it's not so heavy. So sort out everything that has to do with the output on one side, everything has to do with the input on the other side. Then go into the Laplace domain, and that just means everything is just an oscillation, and now it only has an amplitude. So that's why we use here capital Y and capital X, that's the amplitudes. And each derivative becomes a multiplication with S, the Laplace S. So for example here, a second derivative of Y, of the time signal Y, is then the amplitude Y multiplied with S squared. Or minus 3 times Y dot becomes minus 3 times S multiplied with the amplitude Y. Okay, so that's the left side, and on the right side, similar for X, the input. Then you can build the ratio, output divided by input, and that's the transfer function. So we have polynomials in the numerator and the denominator, and then we have to put this somehow into Simulink. There is, for example, the so-called transfer function block, and in this block you can then define the polynomials, and you should just know how to do this. So how to tell Simulink what is the numerator polynomial, and okay, so you just write the coefficients of this polynomial in a vector. So what's important? The square brackets and these coefficients. And don't forget, maybe there could be a 0 inside. For example, here, the numerator is 1 time S squared, but okay. So I just see this is an old. Sorry, okay.
Is that for the top one, isn't it? For the minus 2s squared plus 0s plus 1? I think it is.
Yes, but I don't see this. Okay, so it should be, this should be interpreted as minus 2 times S squared, 0 times S, and 1 times. I think it comes from often reusing these in several exams, and then I did not update this because the denominator is correct. So we have here 1 times S squared, 3 times S, and minus 5 as a constant, so that's okay. But this one here is 1 times S squared. Yeah, you're right, this one is wrong. This one is wrong. But okay, okay, so then let's say this one is wrong. Okay. And up here it's correct. Yeah, you're right. This one is correct. And we have this real minus 2 times S squared, 0 times S, don't forget the 0, and 1 as a constant. Okay. Yeah, okay. So this wasn't wrong. If you did not solve, then use this. Okay, now I must. So you see, we try to write the tasks so that you can solve each one independent of the other ones. So if you're missing values, you could, so either you don't need them or we give replacement values. But actually this numerator then would be 1 times S squared 3 times s plus constant 0, so this will be then 1, 3, 0. Okay. As an alternative to the numerator. Okay. So that's about differential equations. Then a model, for example, here, this has to do with stick and slip. Maybe in the actual exam it will not be stick slip, but something comparable. But it's a model where we have a change somewhere in between. So you will need also a switch, and we have to build then a model from this, from the ideas that you have a balance of forces. And there's an explanation here what the model should do, and then you should be able to reproduce this. It's a bit complex, I know, but honestly, the number of these possible models is very limited. Okay? Just look through the example exercises, and then you see maybe it's 3 or 4 such models. Okay. Okay, and then a last one where we ask them about really MATLAB LTI systems. So there we want you to write something about some script. So for example, we have here a circuit and we want them to define impedances. So you should know what is the impedance of an inductivity or a capacity. Then in these impedances we want to see the total impedance. You need to know their parallel impedances are, well, not directly added. You have to add admittances, so always the inverse values, and serial elements here that you can just add impedances. And then you should plot a Bode diagram of a transfer function. So first it's defined here, and for this transfer function you need to know the voltage divider law. So for serial elements, the ratio of impedances is the same as the ratio of voltages. Okay, so then here we have to calculate the ratio of impedances. And that could look something like this. So first, definition of impedances of C is the function TF. Remember, transfer function takes the numerator polynomial and the denominator polynomial, which is not very complex here. So the numerator is just the number 1. And the denominator is linear polynomial. That means C will be multiplied with the Laplace S, and then we add a 0. So, and 1 over C times S, that is the impedance of a capacitor. And similar for an inductivity L. So then, first of all, we have here a Z out. Okay, so that's these 2 serial elements. You can just add their impedances. So together that is Z out. Then we have Z mechanical probably. And here we have to add admittances, so always inverse values of resistor, C, L, and of course also these output values. So that's this part. What's missing for the Z total, we have 2 more serial elements, RS and LS. So at the end you have to add these 2 impedances also. Okay, so that's the Z total. And then for the transfer function, which takes the ratio of, where is what? H1 is UME, so that's here, divided by U in. So we say this is 1 larger impedance. Everything else is the second impedance, and you have this in divided then first by the first bubble, and then we have this second bubble. Okay, and here across we measure this UME, U mechanical. Okay, and that means we need the Z mechanical. ZME. Okay, and that's why we use here the ratio ZME divided by Z total. Okay, and then the command itself is just bolded. Then the second one, what's the second one? Plus the diagram of U out divided by U in, so that's only across the resistor here. Okay, and that means we have two systems in series, and that means we multiply first this H1, and then this describes how U in is transferred to U mechanical, but then U mechanical is again divided, second time divided, down to U out, and because this is serial, we multiply this with the ratio again, so RL divided by Z out. Okay, careful, this is not the same as only RL divided by U in or only U out. No, you really have to do this product because it's serial. Okay, and that's already everything. So this could look similar again.
So this is the format for the exam, roundabouts. This will kind of look like the exam, this format.
That was really an exam, yeah. This was from 3 years ago, so it's not just warm up, it's really an actual one. And it's just our part here, that means just 50% of the complete exam. So my colleague Ben has another part, and each part yields up to 15 marks. So to sum that will be the complete mark of the exam. Okay, and I think we have 2 hours time for everything. But it's up to you how you use your time for these exams. So there's no minimum points you have to make for any part. Just go as far as you can. Okay, then I think one pair of you, I see them again in the mini project. The others, latest then for the exam. If you have questions in between, you can ask them anytime by email, is the best. And I think Ben and I will do some question and answer hour then maybe 1 week or so before the exam. So maybe we can see also that. Okay, then thank you for your attention and have a nice time.
Huh?